The next important topic is hydrodynamically smooth and rough boundaries. Let's understand when we call a boundary as hydrodynamically smooth and as hydrodynamically rough. Now, as you can see here, we are having a pipe. Here, near the boundary of this pipe, there is a thin layer of fluid where viscous stress predominates. As I had already told you about this, here near the boundary, viscous shear stress is dominating the turbulent shear stress. दिस मीन्स कि हमारा जो फ्लो है वो दो पोर्शंस में डिवाइडेड है. एक पोर्शन विच इज़ नियर द बाउंड्री जहाँ पे थिन लेयर ऑफ फ्लूइड में विस्कस शेयर स्ट्रेस डोमिनेट कर रहा है, शेयर स्ट्रेस ड्यू टू टर्बुलेंस. और दूसरा जो मेरा पोर्शन है यहाँ पे शेयर स्ट्रेस ड्यू टू टर्बुलेंस जो हो जाएगा दैट इज़ मोर कंपेयर्ड टू द विस्कस शेयर स्ट्रेस. तो एक हो गया मेरा पोर्शन नियर द बाउंड्री वेयर विस्कस शेयर स्ट्रेस डोमिनेट्स, शेयर स्ट्रेस ड्यू टू टर्बुलेंस इज़ नेग्लिजिबल. और दूसरा ये वाला पोर्शन हो गया फ्लूइड का जहाँ पे शेयर स्ट्रेस ड्यू टू टर्बुलेंस काफ़ी ज़्यादा है कंपेयर्ड टू द विस्कस शेयर स्ट्रेस. इसको बोलते हैं हम लोग टर्बुलेंट जोन. और जो ये फर्स्ट पोर्शन है इसको हम लोग बोलते हैं लैमिनार सब लेयर. So we can say that in turbulent flow is divided in two portions. First portion उसको हम लोग बोलते हैं laminar sublayer which is near the boundary. और दूसरा जो portion है that we call it as turbulent zone. So we are having two portions, laminar sublayer and turbulent zone. और ये जो इतनी जो height है that we denote it using delta dash, which is the thickness of the laminar sublayer where my viscous shear stress dominates, shear stress due to turbulence is negligible. So this delta dash is thickness of the laminar sublayer. Now let's understand what is the difference between hydrodynamically smooth boundary and hydrodynamically rough boundary. Here, as you can see in the diagram, this are my irregularities and K is the average height of the irregularities that are projecting from the surface of the boundary. This is my laminar sublayer, and here in the second diagram, this one is my laminar sublayer. Then the thickness of the laminar sublayer that will denote using delta dash. Now as you can see in this first diagram, मेरी जो irregularities that is average height of irregularities जो है वो काफ़ी कम है laminar sublayer की thickness की comparison में. That means I can write that my K is less than delta dash. So this type of boundary in which K is less than delta dash is known as hydrodynamically smooth boundary. And in the other diagram, we can see that my average height of irregularities is more compared to the thickness of the laminar sublayer. That is, K is greater than delta dash. तो ये हो जाएगी मेरी hydrodynamically rough boundary. So the first diagram is my smooth boundary and the second one is rough boundary. For smooth boundary, K is less than delta dash. For rough boundary, K is greater than delta dash. And another thing we'll understand कि जो laminar sublayer के ऊपर जहाँ पे flow मेरा turbulent है वहाँ पे eddies formation start होगा. और ये जो eddies है that will try to penetrate the laminar sublayer. laminar sublayer के अंदर आने की कोशिश करेंगी एडीज़ जो फॉर्म होगी वो. और ये जो एडीज़ होती है वो बाउंड्री के पास पहुंचने का ट्राई करेंगी. बट क्योंकि मेरी जो लैमिनार सब लेयर की थिकनेस है वो काफ़ी ज़्यादा है, इस वजह से एडीज़ जो है वो ये जो मेरी irregularities है वहाँ तक नहीं पहुँच पाएंगी, and that is why we call this as smooth boundary, or we can say hydrodynamically smooth boundary. अभी हम लोग अगर बात करें कि जहाँ पे मेरी लेमिनार सब लेयर की थिकनेस इरेगुलरिटीज़ के कंपैरिजन में कम है, तो वहाँ पे ये जो एडीज फॉर्मेशन होगा that will come in contact with this irregularities and lot of energy will be lost. So this type of boundary we call it as hydrodynamically rough boundary. The next thing that we want to see is there are some values which are given by Nicorazzi and Reynolds by which we can decide whether a boundary is a smooth boundary or a rough boundary. Let's just see both of these things. Nicorazzi's experiment and as per Reynolds number. As per Nicorazzi's experiment, it is related with K upon delta dash ratio. If K upon delta dash is less than 0.25, then that type of boundary we call it as smooth boundary. Then 0.25 less than K by delta dash less than 6, then that type of boundary we call it as boundary is in transition. You need to remember two values, 0.25 and 6, and the ratio is of K by delta dash, that is average height of irregularities to thickness of the laminar sublayer. And if K by delta dash is greater than 6, then that boundary is rough boundary. Same way, Reynolds has also given, as per Reynolds, it is U star K by nu. U star, we know that it is the shear velocity, K is the average height of irregularities, and nu, which is the kinematic viscosity. So U star K by nu, if this ratio is less than 4, then we call that boundary as smooth boundary. If this ratio is between 4 and 100, then the boundary is in transition. And if U star K by nu is greater than 100, then the boundary is rough boundary. So for Nicorazzi, K by delta dash, two values 0.25 and 6, and for Reynolds number, U star K by nu, two values 4 and 100. This is what you need to remember. Next, we'll derive the equation for velocity distribution for turbulent flow in smooth pipes and in rough pipes. Velocity distribution for turbulent flow in smooth pipes and rough pipes. Here we'll derive the equation for the velocity distribution firstly in smooth pipes and then for rough pipes. We already know the velocity distribution equation for turbulent flow in smooth or rough pipe, which we had derived, which is U is equal to U star by K log y to the base e plus c. Here one thing we can see from this equation कि अगर मैं y को 0 रखती हूँ तो मेरा जो u है वो आएगा माइनस इन्फिनिटी, बिकॉज log 0 is equal to minus infinity. That is, when y is equal to 0, then u is equal to minus infinity. At the wall where y is equal to 0, then velocity is equal to infinity. So away from the wall, there will be some distance where my velocity is positive. We can say that at some finite distance away from the wall, velocity will be equal to 0. Now that finite distance from the pipe wall, let's just denote it with y dash. So we can say that y is equal to y dash. There my velocity is 0. Placing these values in the above equation, we'll get u is 0. Therefore we'll get 0 is equal to u star by k. In place of y, we'll put y dash log y dash to the base e plus c. So we'll get c is equal to minus u star by k log y dash to the base e. Now we can place the value of this constant of integration in our equation. U is equal to u star by k log y to the base e plus in the bracket minus u star by k log y dash to the base e. So it will be u star by k log y minus log y dash. Subtraction will change to division. Therefore we can write u is equal to u star by k log y by y dash to the base e. Then we also know the value of Kalman constant, which is equal to 0.4. We'll just place that here. U is equal to u star by 0.4, which is equal to 2.5 u star log y by y dash to the base e. Also we can change log to the base e to log to the base 10, which is, we'll just multiply it with 2.3. 2.3 into 2.5 u star log y by y dash to the base 10. This will come u by u star is equal to 5.75 log y by y dash to the base 10. Now for smooth boundary, there exists a laminar sublayer, and as we had discussed that as per the velocity distribution equation that we had found, universal Prandtl's velocity distribution equation, the velocity distribution was logarithmic in nature, but because the laminar sublayer exists, so the logarithmic velocity distribution does not hold good, and the velocity distribution is parabolic in laminar sublayer. So it was assumed that y dash is directly proportional to the thickness of laminar sublayer, that is delta dash. And as per Nicoratz's experiment, he had given the value for y dash, which is equal to delta dash upon 107, where this delta dash is equal to 11.6 nu by u star. Nu is the kinematic viscosity of fluid and u star is the shear velocity. We can just place this. Y dash is equal to 11.6 nu by u star into 107, because delta dash is 11.6 nu by u star. So we'll get 0.108 nu by u star. Now let's just place this here in this equation. U by u star is equal to 5.75 log y divided by y dash is equal to 0.108 nu by u star. U star will go up, so it will be 5.75 log u star y upon 0.108 nu, and 1 upon 0.108, that is equal to 9.259. So we'll get u by u star is equal to 5.75 log u star y by nu into 9.259. Now this multiplication will change to addition. U by u star is equal to 5.75 log u star y by nu plus 5.75 log 9.295, and this log of 9.295 into 5.75 is equal to 5.55. Therefore we get u by u star is equal to 5.75 log u star y by nu to the base 10 plus 5.55. So this is the equation that you need to remember for velocity distribution of turbulent flow in smooth pipes. Now let's just derive the equation for rough pipes. For rough pipes, the main equation that will start from is this one. U by u star is equal to 5.75 log y by y dash to the base 10. But here, as we know that in the case of rough boundaries, the thickness of laminar sublayer will be very small, and therefore it was assumed that y dash is proportional to the height of protrusions, that is the height of irregularities, which is k. And as per Nicoratz's experiment, he had found that y dash is equal to k upon 30 for pipes coated with uniform sand, that is for the rough pipes. So we have u by u star is equal to 5.75 log y by y dash is equal to k by 30. This will be 5.75 log to the base 10, 30 into y upon k. Now we'll take it like that, 30 into y by k. So we can change multiplication to addition, 5.75 log y by k to the base 10 plus log 30 to the base 10 into 5.75, and this log 30 to the base 10 into 5.75, that comes out to be 8.5. So we get u by u star is equal to 5.75 log y by k to the base 10 plus 8.5. This is the equation, velocity distribution for turbulent flow in rough pipes, which you need to remember. The next important topic that we'll discuss is water hammer. Water hammer in pipes. Here we have considered a long pipe which is connected to a tank, and this tank is containing water of height h from the center of the pipe. पाइप के एक एंड पे वाल्व है which is regulating the flow of water. Now I have opened this valve completely. तो जब मैंने ये वाल्व completely ओपन किया हुआ है तब वाटर जो है वो v जितनी वेलोसिटी से पाइप के अंदर फ्लो होगा, और अभी मैं ये वाल्व जो है अचानक से बंद कर देती हूँ. That is, I am just closing the valve suddenly. सडनली वाल्व क्लोज करने की वजह से क्या होगा कि जो मेरा मोमेंटम है पानी का वो डिस्ट्रॉय हो जाएगा और एक हाई प्रेशर वेव जनरेट होगी पाइप के अंदर. अभी ये जो हाई प्रेशर वेव है उसकी वेलोसिटी साउंड वेव की वेलोसिटी जितनी होती है, और वो एक नॉकिंग साउंड क्रिएट करेगी. और ये जो हाई प्रेशर वेव है इसकी वजह से एक हैमरिंग एक्शन होगा पाइप वॉल्स पे, which we call it as water hammer. So here I'll just write this, that the momentum of flowing water will be destroyed and a high pressure wave will be generated. This high pressure wave velocity is equal to the sound wave velocity, and it creates noise which we call it as knocking. Also, this high pressure wave will create hammering action on the pipe walls. This is known as water hammer. ये जो प्रेशराइज होता है वाटर हैमर की वजह से वो कुछ चीज़ों पे डिपेंड करता है, which are, first is velocity of flow of water in the pipe, then length of the pipe, then we have the time taken to close the valve, and also it will depend on the elastic properties of the material of the pipe. Velocity, length of pipe, time taken to close the valve, और जो elastic properties है of the material of the pipe, मतलब pipe material पे भी depend करेगा pressurized due to water hammer. And we are having the cases of water hammer in pipes, which are, we have 3 cases. वाटर हैमर के 3 केसेस होते हैं. फर्स्ट वन इज़ ग्रेजुअल क्लोजर ऑफ वाल्व, Then we have sudden closure of valve. And during sudden closure, we consider two cases. One is that my pipe is rigid, and the another one is my pipe is elastic. These are the three cases. For all of these three cases, we'll see the equation for intensity of pressure wave produced. Let's discuss for the first one, gradual closure of valve. There is also a time limit when we can say whether it is gradual closure of valve or sudden closure of valve. That too we'll discuss. Now here we have considered a pipe AB, which I had shown you in the figure, and there is a valve which is provided at the end of the pipe, which we are saying that we have closed that valve gradually. Instead of closing it suddenly, we are closing it gradually. Then we have area of cross section of the pipe AB, which is A. L is the length of the pipe, V is the velocity of flow through pipe, T is the time in second required to close the valve, and P is the intensity of the pressure wave produced. What is the mass of water in pipe AB? Then mass we give it as density into volume. Volume is equal to area of cross section of pipe into length of the pipe. So we can say that the mass of water in the pipe AB is equal to rho into A into L. And this valve we are closing gradually in time t seconds. So the water will be brought from initial velocity v to zero velocity. तो रिटार्डेशन ऑफ वाटर जो होगा उसे हम लिखेंगे चेंज ऑफ वेलोसिटी अपॉन टाइम, बिकॉज यहाँ पे एक्सेलरेशन नहीं हो रहा है, यहाँ पे रिटार्डेशन हो रहा है, क्योंकि वाटर को हम जो है v जितनी वेलोसिटी से ज़ीरो वेलोसिटी पे ला रहा है. सो इट विल बी चेंज ऑफ वेलोसिटी विच इज़ v माइनस ज़ीरो अपॉन टाइम इज़ t विच इज़ v बाई टी. रिटार्डिंग फोर्स फाइंड कर लेते हैं. फोर्स इज इक्वल टू मास इंटू एक्सेलरेशन, और वी कैन से मास इंटू रिटार्डेशन. So it will be rho AL into V by T. Now we have denoted the intensity of pressure wave produced as small p. So we can say that force due to the pressure wave will be equal to this intensity of pressure wave produced into area of pipe, which is P into A. Now we can equate both of these forces, which is retarding force and force due to the pressure wave. So we get P into A is equal to rho AL V by T. A will get cancelled. P is equal to rho LV upon T. So this is the equation for intensity of pressure wave produced. Then we also have the equation for head of pressure, which we can give as H is equal to P by rho G. P is rho VL upon T, and dividing it by rho G will get rho VL upon rho GT. Rho will get cancelled, so H is equal to LV upon GT. The other important thing that we need to remember is, if we say that the valve closure is gradual, then T is greater than 2L upon C. Here this C is velocity of the pressure wave. T is the time in second, L is the length of the pipe. So if T is greater than 2L by C, then it is gradual closure of valve, and if T is less than 2L upon C, then it is sudden closure of valve. So for gradual closure of valve, we have two important equations. Here let me just make it this as capital H. One equation is for intensity of pressure wave produced, and another one is for head of pressure. Same way, we also want to derive the equation for P for the case of sudden closure of valve and the pipe is rigid. As you can see here in this equation, P is equal to rho LV upon T. When T will be 0, then P will be equal to infinity. Why 0? Because we are closing the valve suddenly. So we can say that our time is 0. Hence P will become infinity. बट एक्सपेरिमेंट्स में से ये ऑब्जर्व हुआ था कि जो प्रेशर जो मेरा होता है ड्यू टू वाटर हैमर वो इन्फिनिटी नहीं होता है, इट इज़ फाइनाइट. When I'm closing the valve suddenly, I have some finite pressure generated. तो इस वजह से ये जो मेरा इक्वेशन है P is equal to rho LV upon T, that is only valid for incompressible fluids and when the pipe is rigid. बट जब भी हाई प्रेशर वेव पाइप के अंदर क्रिएट होगी तो जो लिक्विड होगा वो कंप्रेस होगा और जो मेरा पाइप मटेरियल है वो स्ट्रेच होगा. और इस वजह से फॉर सडन क्लोजर ऑफ वाल्व वी कंसिडर टू केसेस. One is sudden closure of valve and pipe is rigid, and the second one is pipe is elastic. Here we have one thing added, which is K is the bulk modulus of water. अभी जब सडनली वाल्व को हम क्लोज करते हैं तब जो काइनेटिक एनर्जी है पानी की वो स्ट्रेन एनर्जी में कन्वर्ट हो जाएगी. अगर हम लोग फ्रिक्शन इफ़ेक्ट को निगलेक्ट करते हैं तो काइनेटिक एनर्जी जो है पानी की that will be converted to strain energy of water if my pipe is perfectly rigid. So I can say that loss of kinetic energy is equal to gain of strain energy. अभी loss of kinetic energy जो है that is equal to 1/2 mv square, where m is rho al. Therefore it will be 1/2 into rho al v square. Then gain of strain energy. Gain of strain energy is given by equation 1/2 p square by k into volume. So 1/2 p square by k into volume is equal to A into L. Then we'll just compare both of these equations, which is loss of kinetic energy is equal to gain of strain energy. On equating both of these equations, we get 1/2 rho al v square is equal to 1/2 p square by k into al. Now this al will get cancelled and we'll have p square is equal to 1/2 rho al v square into 2k upon al. Now let's just cancel this al. So we have p square is equal to rho k v square. 2 will also get cancelled and p is equal to under root of rho k v square. So we'll have p equal to v root k rho, and this k into, we are multiplying it and dividing it by rho. This k by rho, under root of k by rho, we call it as c, which is velocity of the pressure wave. Therefore we'll get p is equal to rho vc. This is the equation that you need to remember when the pipe is rigid. Now we have the case sudden closure of valve, pipe is elastic. This derivation is not asked, so we are not going to derive it. Few terms have been added here, which is modulus of elasticity of the pipe material, then 1 upon m is the Poisson's ratio and T is the thickness of the pipe wall. Then the magnitude of the longitudinal stress in pipe and circumferential stress in pipe, that we'll just see. And here also we have that the thickness of the pipe is small compared to the diameter of the pipe and the pipe is elastic. We can give the circumferential stress in pipe using this equation, which is Fc is equal to Pd upon 2T. D is the diameter of the pipe, T is the thickness of the pipe wall, and P is the increase of pressure due to water hammer. And then we have the longitudinal stress in pipe, which we can give by this equation. Fl is equal to Pd upon 4T. And then our main equation, which is intensity of pressure wave produced, which is given as P is equal to V into under root of rho upon 1 upon K plus D upon ET. P is equal to V into under root of 1 upon K plus D by ET. This also you need to remember. With this, we have completed all the topics of turbulent flow, and in the next video we'll solve few numericals based on turbulent flow. Thank you.